In addition to nuclear fission, we can produce power by nuclear fusion. In the nuclear fusion, we split the atom. In the nuclear fusion, we can put the two light atoms to form a heavier atom, in this case hydrogen. Nuclear fusion is what powers our sun. The sun is made of gases, hydrogen. At the core is very millions of degrees temperature and very many thousands of atmosphere. At those pressure and temperature, the hydrogen atoms are being fused together to make helium, and the power is produced, which is being radiated outside. Here is constructive to discuss about different phases of the matter. We know the solid, it has a lattice structure. If you heat up the solid, eventually will turn into a liquid, and the liquid eventually turns into the gas. If you heat up the gas eventually to a very high temperature, it causes the ionization. Basically, they knock electron out of the atom, leaving it with a positive charge, which is called the plasma. It is the plasma that can be heated up further and then turned into a form that can be fused together between the atoms of different plasma. In this case, we can have a atom of deuterium, which is made of one proton and one neutrons, with the tritium, which is the one proton and two neutrons. They can fuse together, and all these five elementary particles, they come together, which is very high stable. One neutron is released, and the other four will turn into an atom of helium, and excess energy is produced. If you take two deuterium atom, will turn into helium-3, but for this reaction to take place, we need 400 million degrees Celsius. It's easier to have a deuterium and tritium atom together to form helium-4, and now the temperature drops to 45 million atoms. In the core of the sun, this is not the issue. We have the temperature, but if you want to replicate that on the Earth, that would be a lot of difference between 45 million and 400 million degrees. Therefore, most people are basically trying to fuse the deuterium and tritium on the Earth. It shows that these three reactions compare the deuterium or the fission, fusion, and the coal. You can see from this diagram that for every equal mass of the coal, uranium, and fusion, uranium produces 2 million times more energy than the coal, and fusion will produce roughly 20 million times. For every kilogram of uranium, you need 2,000 tons of coal to produce and then power. We have deuterium in the sea water, but we don't have a tritium in the atmosphere. Tritium can usually be manufactured in the lab by bombarding the lithium with the neutrons. The products is the helium and tritium, and that would be the other component of the fuel of the fusion. There are certain challenges with the fusion. Number one, we need to achieve ignition. That means we have to raise the temperature to several million degrees. Beyond that, which we call it the break-even point, that means the amount of the energy will be given off is more than what energy you put into it. And finally, at that temperature, we need some way to support a fusion reaction in sustained matter, and of course we know that we cannot find any material that can keep that kind of temperature. Way beyond that, the material is destructed. There are different fusion reactors, and I suggest you to read more about it inside the textbook, which is basically two. That the main one is the tokamak, is a Russian basic technology, and we have one in the Princeton University. We have achieved the fusion only for a very small time, short time, about 2 seconds, but we need a much higher time to sustain the reaction. There are other reactors which are like JT60 in Japan, and they were able to achieve the fusion for a longer period of time. One of the problems with the fusion is the confinement, which means that you need to make the reaction sustainable. And there are three approaches to confinement. One is the gravitational confinement, inertial confinement, and magnetic confinement. The gravitational confinement is what happens inside the sun. The sun, the gases is compressed by gravitational forces. It is such a high temperature, such high pressure that cannot be replicated on Earth, and therefore that cannot be done. On the inertial confinement is basically done by the Lawrence Livermore Laboratory in a project they call it NOVA. In this case, there are about 62 lasers, high-powered laser. All of these lasers are shined with a small pellet which contains hydrogen and deuterium, and if all of them are simultaneously, supposedly they will create large enough pressure by compression and high enough temperature that the fusion take place. It is the work under development. They have been able, to do the fusion for a few nanoseconds, but not longer than that. The more conventional method is a magnetic confinement. In this case, the ionized gas is confined to a toroidal path, which is created by the very strong magnet. The gas is being spun around without touching any walls because of the opposite charge between the toroid, the magnetic field, and the gaseous plasma, and eventually they come to a very high temperature and high speed that the fusion can take place without touching any walls. This is the approach is being used in the International Thermonuclear Experimental Reactor, or they call it ITER, which means the way in Latin, and is a cooperation between many different countries: US, European Union, Japan, Russia, China, India, and South Korea. They're expecting to reach the break-even point in 2016, and whether it happens or not, we don't know yet. And they're hoping that by the year 2026, they will be able to have some kind of experimental nuclear fusion reactor to be in operation, producing about 500 megawatt of electric power by that. Whether this happens or not, it remains to be seen. But if nuclear fusion become a reality, that will resolve much of our dependence, to the fossil fuel, and it would be a relatively clean form of the energy source. There have been, in the last few years, some attempts to produce the cold fusion. One of the famous reactions, which proved to be a disaster because it was much of a fusion. About this reaction, it's a cold fusion, is by the two professors of the University of Utah and Southampton, that they claim that they have been able to achieve the nuclear cold fusion inside the lab, but it eventually turned out to be inaccurate, and some people, they think it's never going to happen. There are a few scientists that still feel that the cold fusion is possible. Thank you.